Welcome back, students. In our previous video, I went through the steps of how you draw a Lewis structure when you are given the formula. And so we saw how valence electrons are distributed in the Lewis structure, and how valence electrons can be represented either as a straight line if they are in a shared pair of electrons, which we call a bond, and how we represent valence electrons as dots when they are not shared by the neighboring atom. And we also saw how Lewis structures did not show any three-dimensionality of the species. Everything was laid out flat, and there were no wedges or dashes in the Lewis structure to represent bonds that may have been extending out of or behind the plane of the paper. However, we know that these species do exist in 3 dimensions, and so we need to be able to predict the shape of the molecule or the polyatomic ion, that is, the geometry that they will take in 3 dimensions. So we need a theoretical model that will allow us to predict the shape of the molecule or polyatomic ion from its Lewis structure. And that theoretical model is called valence shell electron pair repulsion. And this is abbreviated VSEPR. VSEPR. So let's think about what this means. Valence shell electron pair repulsion. Well, we know what a valence shell is. It is the outermost shell of electrons. It is the highest energy value, the highest N value of orbitals which have electrons in them. And we call those valence electrons. And we know what an electron pair is. That's when you have a pair of electrons either being shared by 2 atoms, in which case we symbolize it with a straight line, or the electron pair is an unshared pair of electrons, in which case we symbolize it with 2 dots. Repulsion, meaning they repel, because electrons are negatively charged, and negative charges repel other negative charges. So valence shell electron pairs. These are electron pairs that are in the valence level, and they repel each other. So VSEPR, valence shell electron pair repulsion. Now, according to this model, electrons repel each other. So their orbitals arrange themselves as far apart around an atom as possible. So as an example, let's go back to this ion that we did the Lewis structure of, the IF4+ ion. Here we have the Lewis structure, and it shows all of the valence electrons being distributed. Some are in bonds, and some are in unshared pairs. Well, regardless of whether the electron pair is in a bond or is in an unshared pair, the electron pair in this bond is going to repel the electron pair there. And they're going to repel that electron pair and that electron pair and that electron pair. And so these electron pairs are going to do their best to spread themselves out as far apart from each other as possible. And often that means taking advantage of the 3rd dimension to get further away from their neighboring electron pairs. And as they do that, these electron pairs are going to arrange themselves in certain geometries. And the geometries will depend on how many electron pairs we have. So, to determine the molecular geometry, that is the shape of a species in 3 dimensions, we must first determine its electronic geometry. And another way of saying that is, in order to determine the 3-dimensionality of which direction these atoms are all pointing in, we first have to determine the electronic geometry of which direction all of these electron pairs are going to be pointed in. So you can see if we can determine which direction the electron pairs are going to be pointing, and the terminal atoms are attached to those electron pairs, then the shape of this species will be determined by how these electron pairs are repelling each other. So, we are going to determine the molecular geometry or the shape eventually, but first we must determine the electronic geometry. And this is based on the number of electronic domains around the central atom. So what is an electron domain? An electron domain is any single or pair of unshared electrons. So if you have a single electron or a pair of electrons that are unshared, or any type of bond. So a single bond or a double bond or a triple bond, whatever type of bond it is, it only counts as one electron domain. So an electron domain is any unshared electron, either singlet or pair, or any type of bond. So if we go back here and we look at this IF4 plus cation, there is an electron domain right there, that single bond. There is another electron domain, that single bond. There is another electron domain, that single bond. Here is an unshared pair, that is an electron domain. And here is another electron domain, that single bond. So in this case, how many electron domains do we have around the central atom? We have 1, 2, 3, 4, 5. If we look at the cyanide anion, how many electron domains do we have around the central atom, which we determined was carbon? Any type of bond, whether it's single, double, or triple, just counts as a single electron domain. So there's one electron domain, another electron domain. So 2 electron domains around that carbon. And remember, a pair of unshared electrons counts as 1 electron domain. And if we had a rare case where we only had a single electron sitting out here that was unshared, and we call those species radicals, then that single electron alone by itself would also be an electron domain. So an electron domain is a single or a pair of unshared electrons, or any type of bond counts as 1 electron domain, whether it's a single, double, or triple bond. Now in this chapter, we're going to focus on Lewis structures that have arrangements of electrons that occur with 1 central atom and between 2 and 6 electron domains around it. So for example, our cyanide, we had 2 electron domains around the carbon. In the IF4+, we had 5 electron domains around the central atom. So now that you know what an electron domain is, we're going to put this together with our Lewis structure skills, and the sample problem out here gives us an opportunity to practice this 4 separate times. So I've got 4 species. There's water, there's CH2O, which is formaldehyde, PCl3, phosphorus trichloride, and XeF4, xenon tetrafluoride. So I want you to use the steps that you learned in the previous video to draw the Lewis structure for water, and then determine the number of electron domains that are around the central atom. And I would like for you to do all 4 of these eventually, but we're going to do just water first, draw its Lewis structure, and then determine the number of electron domains around the central atom. And that way we can calibrate your method, clear up any mistakes, and then I'll ask you to do the other 3. So right now we'll just do it for water. Pause the video now, and when you're done, resume the video and I'll show you the answer. All right, coming back to this, we're going to generate the Lewis structure for water and then determine the number of electron domains around the central atom. So as always, we want the formula for the species that we're working from. In these other cases, we already have it, but for water, we need to write it because it's not written yet. And we know that water is H2O, right? So we're going to go through our 6 steps and generate the Lewis structure for the water molecule. Step 1, we're going to write the formula and draw the skeletal Lewis structure for this with the least electronegative atom in the center. Well, hydrogen is electronegativity 2.1, oxygen is electronegativity 3.5, so hydrogen is less electronegative. But you remember that there's an exception for hydrogen. Hydrogen can never be the central atom because it can never take more than 2 electrons around it. So in this case, regardless of the electronegativity, oxygen has to be the central atom. So if oxygen is the central atom, then I just arrange the other atoms, the terminal atoms, around it equally. And then I draw a single bond from the central atom out like spokes of a wheel to each of the outer or terminal atoms. There is my skeleton of the Lewis structure. I'm not finished yet, but I have completed step 1. Step 2 says now count up all of the valence electrons that I should have available to distribute. So oxygen has how many valence electrons? It has 8 electrons total, but only 6 of them are in the valence level. And then we have 2 hydrogens. And that's each hydrogen has 1 valence electron, so that's 2. If this were charged, I would have to add or subtract to allow for the charge, but this is not charged. So it looks like 6 and 2 is 8 valence electrons total. Okay? And step 2 also says if I've already distributed some electrons by drawing these bonds, then I have to subtract those because I've already used them. So 4 valence electrons have already been used, and that leaves me 4 more to distribute. We go on to step 3. Step 3 says use any electrons that are left over, and I have 4 of them, to fill the octets of the terminal or outer atoms first. So if these were other than hydrogen, I would start to put pairs of electrons on these outer atoms to fill up their octets. But hydrogen cannot have more than 2 electrons, and it already has those 2 in the bond. So I'm done with step 3. I cannot distribute these electrons to my outer atoms. Step 4, use any electrons left over on the central atom. So I've got 4 of them, and so they're going to go in pairs on the central atom. So I have no electrons left. Step 5, if the central atom's octet is still not satisfied, well, let's check. Oxygen has 2, 4, 6, 8. So oxygen's octet is satisfied, so I do not need to do step 5. Step 6 is only if the species is an ion, and this is not an ion, so I don't have to do step 6. So there is the Lewis structure for water. And you'll notice that I've also shown my math of how I calculated it. Now that I've drawn the Lewis structure for water, I can determine the number of electron domains around the central atom. Oxygen is the central atom. How many electron domains does it have? An electron domain is any kind of bond, counts as 1, so there's 1, 2, and another for this electron pair is 3, and another for that electron pair is 4. So this has 4 electron domains. And I've completed answering the question for water. All right, now that we've gone through that, just as a reminder and maybe help calibrate your method, I would like for you to do the same procedure for all 3 of the other species. For the formaldehyde, CH2O, phosphorus trichloride, and xenon tetrafluoride. Go through each of those, draw the Lewis structures for each one, and then determine how many electron domains are around the central atom in each one. And the reason we're doing this is because we have to determine the electronic geometry before we can determine the molecular geometry. And the electronic geometry is based on the number of electron domains. So we have to have the number of electron domains before we can move on and determine any three-dimensionality of the species. So go ahead and pause the video now and work through those three, and when you're done, resume the video and I will work through this. All right, coming back to this, we have CH2O. Step 1 says I write the formula. Well, it's already written there. And now I draw the skeleton of the structure with the least electronegative atom in the center. The least electronegative atom would be hydrogen, but hydrogen cannot be a central atom. So what is the next less electronegative atom? It's carbon. So carbon is going to be my central atom. And then the two hydrogens and the oxygen will all be terminal or outer atoms. So it doesn't matter where I put them. I just arrange them equally spaced around the central atom. And remember, the skeleton requires that I draw a single bond from the central atom to each of the terminal atoms. Step 2, I count up all my valence electrons that I should have available: carbon, oxygen, and 2 times hydrogen. Carbon has 4 valence electrons, 6 for oxygen, 2 times 1 each for hydrogen is 2. This is not a charged particle, so I don't need to add or subtract any. So 6 plus 4 plus 2 is 12. Total valence electrons. Now I subtract those that have already been used in bonding. 2, 4, 6. Step 3 says I use these 6 to fill up the octets of the terminal or outer atoms. The hydrogens cannot accept any more because they already have 2 electrons around them. So these 6 must be going in pairs on the oxygen, which is the only other terminal atom that can take them. I've filled up the octet for oxygen, and I've used up all 6 remaining valence electrons. Step 4 says use any remaining electrons to fill the octet of the central atom. Well, the central atom is missing electrons. It only has 6 around it right now. So it does need more electrons around it, but I don't have any more valence electrons to distribute. So for step 4, there are no more electrons left to give to carbon. Step 5 says if the central atom's octet is still not satisfied, and that's the case, then we shift to share. So I'm going to take a pair of electrons and I'm going to shift it from this terminal atom where it's unshared right now to being shared. So it doesn't matter which of these pairs I take. I'll take this pair and I'll move it right there to share it. And again, if I had done this in pencil, I would have erased that pair. So now oxygen has not lost electrons. It still has 2, 4, 6, 8 electrons around it. But by sharing that pair with carbon, now carbon has a satisfied octet, 2, 4, 6, 8. So shift to share, and that satisfied the octet of the central atom. Step 6, this is not an ion, so I don't need to put brackets or charge around it. And I'm finished. Now I have to determine the number of electron domains. And so here we go. On the central atom, carbon, I have any kind of bond. Any kind of bond counts as 1 electron domain. So here's a single bond that counts as 1. Here's another single bond that counts as another one. Here's a double bond that counts as 1 domain of electrons. So how many electron domains do I have around carbon? 1, 2, 3. 3 electron domains. Moving on now to PCl3. Draw the skeleton. Phosphorus is less electronegative than chlorine. If I didn't know that, I could look it up. You're not expected to memorize their electronegativities, so you would have had to look them up. Single bond from the central atom to each of the terminal atoms. There's the skeleton. Now I calculate the valence electrons. Phosphorus has 5, 3 chlorines of 7 each. So the total, there's no ion that has to be considered here. The total here, 5 and 21 is 26. minus the 2, 4, 6 that I've already used. Leaves me 20 electrons that now have to be distributed. I begin by putting them on the outer atoms first, evenly and in pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18. I cannot put any more on the outer atoms. Outer atoms can never exceed 8. Remember, it's only when certain atoms are acting as central atoms then they can exceed their octet. But these chlorines right now, since they're acting as outer or terminal atoms, they cannot exceed 8. So I've distributed 18, and it leaves me 2 left. Those go on the central atom to satisfy the octet of the central atom. So there's my Lewis structure for PCl3. How many electron domains do I have around the central atom? 1, 2, 3, and that electron pair right there is 4. So 4 electron domains. Moving on for xenon tetrafluoride. Xenon has a lower electronegativity than fluorine. How do I know? Well, fluorine has the highest electronegativity of everything. Single bonds for my skeleton. Step 2, count all the valence electrons available. 4 times fluorine, which is 4 times 7 for each fluorine, which is 28. Xenon has 8. No ion charge to deal with, so 28 and 8 is 36 valence electrons total. 2, 4, 6, 8 have already been used. 28 electrons remain to be distributed. Step 3 says put them on the outer atoms first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Oops, I should have distributed 2 more up here, right, to fill in that octet. So I should have distributed 24. And that now leaves me with 4 electrons. By the way, that's one of the biggest potential sources of error that you're likely to make when you're doing a Lewis structure, is losing track of your electrons and ending up having too many or too few electrons, and you'll end up putting on the central atom when you shouldn't. So be careful about that. You just saw me make the mistake, but I was able to correct it. So I've got 4 electrons left. The octets of the terminal atoms are satisfied, so they can't go there. So these 4 electrons go in the central atom, there, and there, just so that it's obvious that they are associated with that xenon. The central atom is octet satisfied. In fact, it has exceeded its octet, which it's allowed to do, by having 2, 4, 6, 8, 10, 12 electrons around the central atom in this case. So there is no need to shift to share any pairs of electrons to satisfy xenon. So we can go on to step 6, and this is not an ion, so it is not required to have brackets and a charge around it. So there's the Lewis structure for xenon tetrafluoride. How many electron domains are around the central atom? 1 for each type of bond. So you got 1, 2, 3, 4 for the single bonds, and 5 for the electron pair there, and 6 for the electron pair there. So I've got 6 electron domains. And that is how we determine the number of electron domains. So hopefully this gave you some practice on drawing Lewis structures. And once you draw the Lewis structures, then you can determine the number of electron domains that are around the central atom in that Lewis structure. So you have to draw the Lewis structure before you can get this answer, because only the Lewis structure will tell you how many electron domains are around the central atom. Once you know the electron domains, the number of electron domains, then based on that number, you can determine what geometry those electron domains are going to take. and that we will cover in the next video.